So moving on to the next presentation, we are coming back to the research centers again. We have Tristan Erion-Lorico, who is a VP Sales and Marketing at Kiwa PVEL, and he is going to talk about PV module reliability trends. Tristan?
Hey, thank you.
Yours.
You can see my screen okay, and you can hear me all right?
Yeah, everything is good. Good to go.
Perfect. Well, thank you for the introduction. As you said, my name is Tristan Erion-Lorico, VP of Sales and Marketing at Kiwa PVEL, and I'd like to thank the Taiyang team for having me. I'm based in Toronto. It's quite early here, just 8 a.m., but I was able to watch the last 3 presentations and found them informative. So congratulations on putting another good conference together here. So Kiwa PVEL, for those of you who don't know us, we're formerly called PV Evolution Labs. We're the independent lab of the downstream solar market based in California, USA. Our mission, since our founding over 10 years ago, we create data that matters for solar adoption. And we're probably best well known for our product qualification program, which goes into our PV module reliability scorecard. I'll touch upon that shortly. As you can see, we provide a wide range of services. They're all to advance our mission, which is to advance solar adoption. We work with companies all over the world, including banks, developers, asset owners, insurers, and they all use our data to help de-risk their procurements and projects. So you can learn more about us at kiwa.com/pvel. And we're part of the Kiwa Group. If you're not familiar, it's a global testing, inspection, and certification company based in the Netherlands. There's over 10,000 employees that are focused on a variety of industries, but specifically to solar, you can see in that graphic there that our services range from technical advisory, module testing, inverter testing, factory and field inspections, engineering, and we also offer market intelligence. And we really enjoy being under the same parent company as our colleagues at Kiwa PI Berlin. For those of you who were here at the very start, my colleague Stephen presented some information that we recently released that I'll touch upon that later as well. So now on to our product qualification program, or PQP. This is the industry-leading extended reliability and performance testing protocol. Manufacturers sign up for this testing, and with their approval, we share their results with the downstream side of the industry. So module buyers can access those results. Those are typically, the people accessing the results are typically subscribers to our premium partner program, which I'll touch upon at the very end, just for a moment. So this means that the PQP helps manufacturers reach new customers, as well as having a trusted third party to demonstrate their quality, and also helps module buyers get the data they need to de-risk their purchases. It's great to have manufacturers talk about how good their products are. It's better when an unbiased third-party lab talks about that. And as stated here, the PQP is regularly updated and covers a wide array of module failure mechanisms. We iterate much faster than IEC standards to ensure that our testing is relevant to new module technologies and failure modes. And our testing goes well beyond the requirements of IEC 61215 to better vet module designs and bill of materials or BOM combinations. I won't go through each of the tests here, but you can learn more about them at kiwa.com/pvel/PQP. And that brings us to our annual PV module reliability scorecard, which is released in the spring each year. This year was the 10th edition. We're quite proud of that, and included a new top performer category for the hail test, a higher bar for LID and LETID top performers. We also changed the scorecard design to better highlight manufacturers that achieve top performer status in multiple categories. And we had some other updates. We released it on June 5th and have had over 35,000 unique visitors to the scorecard website from this is a fact I love, an astonishing 160 countries is where those visitors are coming from to read the scorecard. So that definitely shows the wide-ranging interest people have in module reliability, the topics being discussed today and tomorrow with this Taiyang conference, as well as how influential our test results are for purchasing decisions around the globe. We've got a large breadth of manufacturers participating in our PQP testing. This year, we had 53 manufacturers named as top performers. So having this level of popularity means that we can benchmark PQP results across suppliers. That's possible and encouraged. It also means our test results and the insights from them are meaningfully representative of the current module technology across the majority of module manufacturers. We're not just taking a few results from a few manufacturers and saying, hey, this is how modules perform. It's really a wide range of manufacturers that we're testing. And another call to action, you can learn more and visit the scorecard for free at scorecard.pvel.com. Okay, thank you for allowing me to go over those introductory slides. Now to the real part of the presentation, the test results. So for the next many slides, I'll focus on testing trends, typically results across cell technologies tested at the module level, and also providing often an example of when things went wrong with module reliability in our testing and when we uncovered an issue. So first up is thermal cycling. So we got the box plots on the left and an example on the right. Here for this test, the module is subjected to 600 thermal cycles from -40 up to +85 degrees Celsius. This test helps identify cell soldering and metallization issues, as well as junction box reliability concerns. You can see the results here across PERC and TOPCon are generally aligned. However, as reported in the 2024 scorecard, 5 TOPCon bombs recorded a power degradation failure before they reached TC 600, as opposed to just 1 PERC bomb. So there is slightly higher risks for TOPCon. Those TOPCon degradation failures were often due to cell metallization issues at the last soldering point on the cell, which makes a dark horizontal line in the EL images. You can see that on the right, all those lines at one edge of the cell. We saw that on a number of TOPCon modules. And while there's a larger range for HJT bombs, you can see that box plot is much larger. Of course, the sample size is much smaller. We're testing far more TOPCon than HJT. That range is from the last 3 years. These test results are from, as it says, Q3 2021 to 2024. We've actually seen recently thermal cycling improvements in HJT bombs produced in 2023 versus from previous years. But I'd say there's still reliability risks are higher for HJT, while manufacturers dial in the necessary low temperature soldering process. The cell soldering for HJT is much different than for PERC and TOPCon, and some know how to do that reliably. Others are still have some work to do. Okay, on the damp heat side, so for this test, module subjected to +85 degrees Celsius and 85% relative humidity for 2,000 hours. That helps reveal corrosion and or delamination issues in susceptible modules. We heard about that a couple of presentations earlier. So again, PERC and TOPCon results are also aligned in this test, while HJT, just as the last one, has a wider range of results from 0.6% degradation up to 6%. As we reported in this past scorecard, 11% of bombs we tested experienced 1 or more damp heat related failures due to delamination, the junction box lids falling off, electrical insulation faults, and then lastly, power loss. You can see one of those delamination faults in the image on the right, where there are small bubbles around the transversal ribbon, even extending to the cell. So these types of bubbles are on the rise in our testing. We used to see them like 10 years ago, then they went away for quite some time. And in the last maybe 18 months, we're seeing them more. they're definitely indicative of poor lamination quality, and we think it's in some cases it's due to using thinner encapsulant. So as manufacturers are getting squeezed on price, they are getting encapsulant that's thinner, and there's not enough material there. So during our testing, that delamination creeps in from the edges. This defect might look somewhat innocuous, but it's quite serious because it reduces the electrical insulation between the ribbon here and the cell circuit and the frame. And typically on a 1500 volt module, that's 1500 volts between those 2 points. So what can happen is electrical arcing between those, which is a fire risk and a huge module reliability risk. So this growing trend is quite concerning. Onto the mechanical stress sequence. Here we do 3 rounds of static mechanical loading at 1800 Pascal using either tracker mount or corner mounting. And then we follow that with 1,000 cycles of dynamic mechanical load at 1,000 Pascals. After that, modules are subjected to 50 thermal cycles and 10 cycles of humidity freeze. Using that tracker mount is part of the PQP update that came out a year ago. Before that, we were using the two rail mount at 2400, and now we've switched to tracker mount at 1800 Pascal. So this test obviously is to validate the durability of mechanical durability of modules and their susceptibility to cell cracking related power loss. For this test, we see negligible cell technology impacts. You can see, HJT is a little behind the other two, but they're all fairly close. And while degradation rates for this test are fairly stable, module breakage rates during SML and DML have been on the rise. That's shown in the picture on the right, where we broke a module in half when it mounted on a 400 millimeter next tracker rail. That module exhibited a high amount of deflection before it broke, and it's got a 30 millimeter frame that just could not protect against that amount of deflection. And while this example broke during SML, we find the combination of SML plus DML is key, considering we have other examples of modules breaking during DML after the initial stress of SML. Those bombs that broke during DML would probably not fail at SML only or DML only. It's really both those tests that show the mechanical durability weaknesses. We've also just started a number of PQP projects with very large modules. That is those that are 2382 or 2384 millimeters. We've been testing those for a while, number of years, but we're finding more and more of them coming into the lab now. And on a bunch of them, the frame wall thicknesses are below nominal specs. So manufacturers, cost-cutting measure again, are removing some of the aluminum, going to thinner walls, thinner channels in the frames. And it's all to save costs, but it creates mechanical durability risks. So it's likely we'll be seeing more module breakage in this test in the weeks and months to come. Okay, next up, potential induced degradation or PID. We heard about this a couple presentations ago. During this test, modules subjected to those damp heat conditions again, plus we apply maximum system voltage, typically 1500 volts, between the frame and cell circuit. The test lasts 192 hours. We don't see statistically different results between PERC, TOPCon, and HJT, or really even between glass and glass backsheet modules in this test. It doesn't seem like the cell technology or the laminate type is a big driver. But as we reported in the scorecard, encapsulant choice does matter here. We tested 3 bombs from the same module manufacturer using the same cells, but with 3 different encapsulant suppliers. And we got 3 different results. So on the first, it was 1.1% degradation. Next was 2.6, and the third was 3.3. So, a tripling in the PID resistance between 2 encapsulant suppliers. So that shows how important the material selection is, and that we need to test specific bombs being deployed to site. Don't accept a test report on encapsulant A and then they deliver encapsulant C to you and say, oh, it's all the same. It's not the same. And we see that in our testing. We also reported in the scorecard that 11 manufacturers experienced at least one failure, many due to PID polarity, which we heard about earlier as well. That's often reversible with a UV exposure. A case of extreme polarity is shown on the right there with 15% degradation after PID. Most of that recovered during UV exposure, but the field relevance of the degradation and recovery still needs to be researched. And just because it recovers under UV, I wouldn't say you can dismiss all of that degradation. And there's some papers that speak to PID polarization happening in the field. Okay, switching over to our hail testing. I'm switching the slide design a bit, but for this test, we impact two 2mm glass modules with 40mm hail. If there's no glass breakage amongst those first two modules, then we test two more at 45mm hail. If there is glass breakage at 40mm, then we retest two at 35mm. We do the similar approach for glass backsheet modules or hail hardened glass designs, but we would start at 50mm, go up to 55 if no breakage, or go down to 45 if there was breakage on the original two samples. So we're really testing 4 modules and looking at the point of failure. The graph on the screen is taken from the scorecard. It shows breakage rates for 2mm glass modules compared to 3.2mm glass backsheet. And at 50mm, you can see that 89% of 2mm glass modules experience glass breakage, but that drops by more than half to 40% of modules experiencing breakage for 3.2mm glass backsheet. So that speaks to the durability of glass backsheet versus glass, particularly 2.0mm glass, and why some might consider the Endurance transparent backsheet versus glass, especially in hail regions. Shout out to the previous presenter that talked about that. And on the right is a glass backsheet module that didn't experience glass breakage with 50mm hail. You can see that there are some pretty significant cell cracks there. And while they look quite ugly, multi-busbar modules have shown high resilience to power loss due to hail impacts. The power loss of this module post-hail is just 2.44%, which isn't zero, but it's a lot better than some may assume. And as we reported in the scorecard, we haven't seen any hail power loss greater than 3%. And we also see negligible cell technology impacts in this test. I'm just realizing that I'm short on time, so I'll speed it up a bit. LID, LETID, this test is pretty boring. For the sake of time, I'm just going to say we've pretty much solved this for gallium-doped PERC and N-type modules. We see degradation typically less than 1% on all of those. And check the scorecard to learn more about the trends we're seeing there. But really, this test, not so relevant anymore. Test that is relevant that we heard about in a couple of the previous presentations is UVID testing. It is certainly not boring. The box plots here are taken from our UVID poster that we presented at IEEE PVSC. I encourage you to access that full poster to learn more about UVID and how it can occur, although we heard about that in the previous presentations. Allow me to quickly summarize what we're currently seeing, that there are multiple UV-induced degradation mechanisms that we and the industry are working to better understand. In some cases, UV light is permanently damaging layers within the cell, leading to permanent power loss. But in other cases, the UV light triggers instabilities in the cells, which can be recovered in various ways, likely including a short exposure to full spectrum light and or to high temperature. So we're still learning about that recovery process. But because it recovers, especially in full spectrum light, we're working to determine how field relevant the initial degradation is. And we've got modules outdoors that were susceptible to UVID in the lab. We're seeing if they're susceptible in the field. But it looks like some of this degradation is really instabilities in the modules as opposed to permanent degradation, which we're also seeing. So, you know, it's still a relevant test, but we need to learn more, both as PVEL and as an industry. But in the meantime, we see some modules have very little UVID in our test, and those are probably ones that you'd want to gravitate towards as the industry figures out exactly what these mechanisms are and how permanent the degradation is. Okay, just quickly onto performance testing, our PAN results. I want to go through this quite fast. PMP, temperature coefficients on the left here. You can see in our data, not a lot of HJT modules, but HJT is better than TOPCon, which is better than PERC. So N-type technologies, definitely better temperature coefficients than P-type PERC. For low light performance, we really don't see a difference, huge difference in the cell technologies. You know, we don't see an inherent improvement in TOPCon versus HJT versus PERC. Yeah.
Can you please wrap it up in a minute?
Yeah, sure. And then bifaciality, we see that PERC is 75 or 70% plus or minus 5. TOPCon is really 75 plus or minus 5. A lot of TOPCon data sheets say 80%. We don't see that in our data. And then final test results in our IAM test. We spent about 18 months developing this IAM test. And we see that often the results, often the results intersect the PVSys default for AR coding. So we're not, you know, we took out most of the sources of uncertainty on IAM, and we're not seeing the big differentiators between bombs on our IAM test. Turns out once you remove a lot of the measurement uncertainty, a lot of modules perform similarly to the AR coding default. That said, the difference between the lowest performer and the highest performer is about 0.5% in terms of energy yield. So it's still valid to do the test because 0.5% matters. But some of these IAM curves that look like a square wave, we're not seeing it in our data. Our data does not support that. And then I included a few slides on the white paper. I know Stephen covered this already. Check it out. It's at kiwa.com/raisingthebar. We talk about what to accept for PQP test results and what additional testing to do as far as batch testing and ongoing reliability monitoring. I spoke too long about the test results and didn't have time for this, but please check Stephen's presentation as well as the Raising the Bar webinar. And if you're interested to learn more, please sign up as a premium partner. We've got lots of leading companies that are using our data to make procurement decisions. We get quarterly data to them. A lot of the data I covered came from the recent presentation on that. You can learn more there, kiwa.com/pvel/PPP for premium partner program. All right, sorry for going over. Thank you for your time, and I look forward to the Q&A session.
Great. Thanks a lot, Tristan. I don't know, for some reason I cannot start my camera, but anyway, I think we will have the questions round in the in our panel. So please answer the questions if there are any in the chat window.
Understood.
And so yeah.